All right, so let's look at this example where we need to determine the diameter that a helium-filled balloon has to have to float with neutral buoyancy. And we know one thing: the mass of the empty balloon is 2 grams. All right, so it's pretty cool that we're going to be able to figure this all out knowing or given just one quantity. That being said, we'll have to look up some densities here, but anyway. So getting started here, we've got a balloon. That's not a very good balloon. All right, there's my balloon. What's really nice about this balloon, it's perfectly spherical. All right, that's the great thing about physics. We deal with ideal shapes. So we have a perfectly spherical balloon. The thing we have to be careful about here with the balloon is that it's not uniform density, right? We've got the balloon shell, so probably made out of some sort of rubber or latex or something like that. And then we've got inside of it, well, balloons typically are going to be filled with helium. That does not look like the word helium, does it? There we go. That's a bit better. All right. So if we're drawing, let's say, a free body diagram, right? Well, we'll just talk about the forces here, right? We've got the weight of the balloon itself, which we're told its mass, so that's pretty useful. And then we've got the weight of the helium, and that's all going to be offset by the buoyant force, right? So if we're kind of sketching out free body diagram, I don't know if these vectors are correctly proportioned, but we've got buoyant force upward, we've got the force of gravity of the balloon itself, the rubber, and then the force of gravity of the helium inside the balloon. All right, so let's write an equation then, right? We're applying Newton's second law. So we've got, sorry about that. We've got the weight of the balloon plus the weight of the helium, so that's the mass of helium times g, is equal to the weight of the fluid displaced. And the fluid displaced here is going to be air. So it's the mass of air times g. Right. You might write this equation a little differently because we know a couple things, right? So we know we can rewrite very overtly, right? Because this is just the buoyant force. I wrote it a little bit more inherently. But this is simply just the density of air times the volume of it, the air displaced. Sorry, I keep popping up that thing. Here, knowing the mass of helium, well, we don't really know much about the size and shape of this balloon, except for that it's a sphere. But the density of helium is going to be something constant. So we'll write this as the density of helium times the volume. Well, here we're dealing with basically is the volume of the balloon, which is actually going to be the volume of air displaced. And we don't need to replace the mass of the balloon because we're told that's 2 grams, which we will be converting that to kilograms. So looking at this here, we've got g in each term, so those will cancel out. So we have the mass of the balloon plus density of helium times the volume of the balloon is equal to density of air times the volume of the balloon, because the volume of the air displaced is equal to the volume of the balloon. Here we're assuming that the balloon material itself, rubber or latex or whatever it is infinitely thin, right? It doesn't have much of a size. All right. So looking at this here, we can do a little bit of math here. I'm going to have the mass of the balloon equal to the volume of the balloon times density of air minus density of helium. All right, those are 2 known quantities. I'll write those off to the side here. Density of helium, you can look up in a table, 0.179 kilogram per meter cubed. And the density of air is 1.28 kilogram per meter cubed. All right, so those are known. The mass is known. So the only thing unknown here is the volume of the balloon. This is useful because what we're trying to solve for is diameter. All right, so if we can rewrite the volume of the balloon in terms that include that diameter, then we're basically now just rearranging and solving. All right, so looking at this, well, we can rewrite volume. Well, volume, we're dealing here with the sphere. Volume of the sphere is 4/3 pi r cubed. All right. And then I'm going to take the extra step, right? We could right now actually solve for radius and then just double it to get diameter, right? But I'm going to do the pretty math thing of replacing radius with half diameter. So we've got mass of the balloon is 4/3 pi diameter over 2 cubed. All right, so now it's just a math exercise here, a little bit of algebra. So divide by the densities on both sides. That leaves us with 4/3 pi d cubed over 8. And that simplifies to pi over 6. Is that right? I think so, right? Okay. So then that leads us to rearrange for the diameter. That will end up being 6 over pi times the mass of the balloon over density of air minus the density of helium. All that to the 1/3 power, since we're doing a cube root. And plugging that all in, and here just make sure we're converting mass to kilograms. And that ends up giving us 0.15 meters. So that would have to be the density of the diameter of the balloon in order for it to have neutral buoyancy in air.